All right, guys, so let's go over the quiz. I tried to do it all up here ahead of time. So if you just want to pause and like zoom in on any particular spots, you can ignore me going over this entirely. Let me kind of step to the side here real quick. But I'm going to cover them in order. For starters, if you were to throw a sad muffin in the air, how does its distance compare to its displacement? And use a picture. Well, I've just shown the picture and I was going to explain it to you with words. The velocity is up, and you can see that the distance is the total distance of the line traveled. Like we could figure out, basically, if we calculated the displacement up and the negative displacement down and added those both together without signs, that would be the total distance. In other words, if displacement up was, say, +8 and displacement down was like -10, which you can see because it hits the ground, that would mean the total distance would be 18. But the displacement is a straight line path from where it began to where it ended. So if I just use those numbers that I just did, the 8 up, 10 down, the displacement from the beginning to the end does not care about the distance and would just simply be a -2. If I put some numbers to it, let's say that is 0, let's say that is 2, and nothing is to scale here because according to that, that would be position 10 right here. 8 on the way up, +8, -10 on the way down, but overall, the entire path from here to there would be a displacement of -2 in that particular case because it doesn't care where the distance actually was. On to number 2. Okay, in number 2, you throw a dead swallow in the air. Throw it up at 12.2 meters from a height of 2.1 meters. You'll notice, if you can see carefully there, that I've established that that is already position initial. I used different colors here. The 12.2 was to signify the initial velocity. I have another arrow here signifying the original displacement on the way up. Because the first part of the problem asks how high does it go? And we know an initial velocity of 12.2. If we just worry about this first section right here, we would know that the final velocity at the top has to be 0, and acceleration is -g. This is the equation you'd use. You'd cancel VF, VI, -VI would move over. Sorry, -VI squared. As we commented before, the square does not affect that negative because it's not within the parentheses itself, which is a good thing. Because right over here, when I plug in the positive 12.2 and square it, again, that doesn't cancel the negative, but the negative does cancel with my -g right down here to give me a positive 7.6 meters. But I have to remember that that's displacement. And the question asked is, what is the height total? So the height final is the height initial plus change in height. I switched out x's for h's, same thing. The original height is 2.1. The displacement was 7.6, so the final height should be 9.7. Now the last part says how much total time it was in the air. You have a couple ways of potentially doing this, as we've discussed previously. The first thing that you could do is, since this is just the way up, you could of course just calculate this amount of time right there. And then you could make a whole new set of variables for the way down and calculate the time with that. Had you done that for the way down, velocity initial would still be 0 at the top, acceleration would be -g, and the displacement would be -9.7 meters, and then you could try to find time. You could, by the way, go straight for that time without using quadratic, which a lot of people avoid now that they've seen that it somewhat comes up, and that's because the 0 cancels one of the terms. I did not do it this way. I didn't calculate this and add them together. Instead, I looked at the entire path from here all the way up, straight down. The initial speed of the entire path is 12.2 that we start with here. Gravity the entire time is -g, and the displacement, as we discussed over on -1, is a -2.1 because it starts 2.1 meters above the ground. I then use this equation, and I do, in fact, have to use the quadratic in this particular case. You don't have to show this. It can be helpful. I like showing it when I'm doing problems that standard form so you can see kind of where they're coming from. X squared to t squared, x to t, and c, the term that doesn't have any. Keep in mind this is plus c, so I actually had to move this to the other side to set it equal to 0. That's why that says negative displacement. So I have a negative 2.1, which gives me a c value of positive 2.1, a b value of 12.2, and an a value of -4.9 meters per second squared. Here's your equation for the quadratic. Once again, you don't have to show this, but again, it can be helpful so you don't make any mistakes. I come here and I just plug in those numbers just said. The two numbers that spat out were a negative 0.16, which obviously I know is not the right answer, and a positive 2.65, which should also have been your answer if you had gone up and down, separated them, and add them together at the end. Another quick reminder, if you did want to do the quadratic, again, there is a way to avoid using the quadratic specifically in this particular case, and that is you could solve for velocity final first with this equation right here. One thing you would have to be careful of, though, is since there is a square root, you would absolutely need to remember that plus or minus, because this absolutely should be a minus, and if it isn't, it's going to give you actually the incorrect answer of 0.16 negative, which is obviously not going to be correct, so be careful with that. Finally, number three. Oh, I'm sorry, my apologies. At the end of number two, I'm gonna run away from it. And at the beginning of number three,
reluctantly crouched at the starting line.
Here we go. So on number three, we have a car that's going to be distracting.
Flashes, the flags go.
We have a car that is taken off, it says, for a quarter mile. Then, after the quarter mile, it begins to brake. So that immediately tells us there are two separate accelerations in this problem, and the variables must be split. If you only have one set of variables, it is 100% impossible to get the correct answer of this particular problem. It just does not work. So we have the car when it's speeding up, where I wrote down that the acceleration is pointed the way it's going, and then when acceleration is the opposite way, or when it's braking. So it starts off at 0, accelerates at 6 meters per second squared for 400 meters. Of course, that number was not said in the problem, but it said quarter of a mile and reminded you that a mile was 1,600 meters. Technically 1,609, but we're not going to get particular on that. And I like to set up all the variables at the very beginning. The braking section, we don't know what the velocity initial is, although it will be the final velocity of the first section. We do know that it's going to end up stopping because it says it took 600 meters to stop. So a lot of people, when they do this wrong, try to just smush those together and give 1,000 meters in that section. But since the acceleration changes, it's 100% going to spit out a wrong answer in that particular case. So our total time is going to be the time of the first one plus the time of the second one. Unlike with the last problem, there is no way to combine these two together since it is different accelerations. So I have to calculate them separately. So you can use different equations here if you go in a slightly different order. I calculated time first by using this equation. You'll notice my second term cancels, no need for the quadratic. I just multiply by 2, divide by a, and then square root, plug my numbers in, and I get 11.5 seconds for the first one. With that 11.5 seconds, I come right over here, use my basic velocity final equals velocity initial plus acceleration times time. Velocity initial goes to 0 because there is no velocity initial. So it's just the acceleration of 6 meters per second squared times 11.5 seconds. So my velocity final at that 400 meter mark, or that quarter mile, is going to be 69.3 meters per second, which in turn is going to be the initial velocity right here. 69.3 meters per second. You don't have to, by the way, plug these back in up here. This is just me trying to help you see where stuff goes. Because I have that, I now have 3 variables trying to find the time. If I go straight for it, I'm going to use this equation right here. Velocity final will cancel. So a little bit of algebra. 2 times delta x over vi gives me delta t2. Plug that all in, you get 17.32, roughly 17.3. Add that with our original time, we get that the total path was 28.8 seconds. You could have gone in a slightly different order of equations. You did not have to exactly use the equations I used, for example, right here. If you wanted to find velocity final first, you would have actually used the vf squared equals vi squared plus 2a delta x. Then to get time, I probably also would have used this one here. Just take vf and divide by a. That should also spit out 11.5 if we've done that correctly. And then more than likely, you would use this one if you want to go straight for it, although again, you could technically find the acceleration with the vf squared equals vi squared plus 2a delta x, and then use that to get delta t, but there'd be no reason necessarily to do that unless you wanted to find that out for that section. That's That's how you do the quiz. Maybe?
Churning and burning, they yearn for the cup. They deftly maneuver and muscle for rank. Fuel burning fast on an empty tank. Reckless and wild, they pour through the turns. Their prowess is potent and secretly stern. As they speed through the finish, the flags go down. The fans get up and they get out of town.